Hello, my name is Dörte Fischer. I'm a PhD student at the University of Oldenburg in the signal processing group of Simon Doclo. It's my pleasure to welcome you to my presentation for the fully virtual ICASSP 2020. I will present our work about estimating the normalized speech correlation vector for single microphone multi-frame Mvdr filtering using subspace decomposition. In our work, we consider a single microphone system, where a speech signal is degraded by additive background noise, leading to a reduced speech quality and speech intelligibility. To improve the speech quality and intelligibility, speech enhancement algorithms are required. Exploiting that speech is highly correlated over time, we use a multi-frame signal model in the short-time Fourier transform domain, where speech correlation across neighboring timeframes are exploited. The main objective of this work is to improve the accuracy of estimating the speech correlation vector using subspace decomposition. Typically, single microphone speech enhancement algorithms are implemented in the STFT domain, where the noisy speech STFT coefficient y at a frequency band k and a time frame m is given by the complex value speech STFT coefficient x and the complex value noise STFT coefficient n. It is typically assumed that neighboring STFT coefficients are uncorrelated over time. So to estimate the speech STFT coefficient, a real-valued gain h is applied to each noisy STFT coefficient independently. For single frame approaches, typically a frame length of 60 up to 32 milliseconds is used. However, it is well known that speech is highly correlated over time, such that it is more realistic to assume that neighboring STFT coefficients are correlated over time, especially to exploit the speech correlation over timeframes. Hence, by stacking the current as well as the L-1 previous timeframes of the noisy speech STFT coefficient into a vector, the noisy speech vector y is given by the sum of the speech vector x and the noise vector n. To estimate the speech STFT coefficient in multi-frame approaches, a complex valued FIR filter is applied to the noisy speech vector y. For multi-frame approaches, exploiting the speech correlation over time, typically a frame length of 4 up to 8 milliseconds is used. To exploit the speech correlation across timeframes, it was proposed to decompose the speech vector x into temporally correlated speech components and temporally uncorrelated speech components, where gamma x is defined as the highly time-varying normalized speech correlation vector, representing the speech correlation between the current and previous timeframes with respect to the current speech STFT coefficient x. So it can be computed by normalizing the first column of the speech correlation matrix Rx to its first entry, such that the first entry of the normalized speech correlation vector is always 1. Using this decomposition of the speech vector x, a multi-frame signal model was proposed, given by the correlated speech component, the uncorrelated speech component, and the noise vector n. Similarly to the well-known minimum variance distortionless response beamformer, the single microphone multi-frame Mvdr filter was proposed by Wang and Benesti. This filter aims at minimizing the total signal output power while not distorting the correlated speech component, where Ry is a noisy speech correlation matrix. Solving this optimization problem yields to the multi-frame Mvdr filter. This filter depends on the noisy speech correlation matrix Ry and the normalized speech correlation vector gamma x. We showed at the IEEE 2017 that the performance of the multi-frame Mvdr filter is highly sensitive to estimation errors of the normalized speech correlation vector. While the noisy speech correlation matrix can be directly estimated from the noisy speech signal by using, for instance, recursive smoothing, estimating the highly time-varying normalized speech correlation vector is difficult. In the following, we will discuss two estimators for the normalized speech correlation vector. First, the state-of-the-art maximum likely estimator, and then the proposed estimator based on subspace decomposition. So assuming that the speech and noise signals are uncorrelated, we can define the noisy speech correlation matrix by the speech correlation matrix Rx and the noise correlation matrix Rn. Using this formulation, the normalized noisy speech correlation vector can easily be defined as a function of the normalized speech correlation vector gamma x and the noise correlation vector gamma n, as well as of the a priori SNR C, defined as the ratio of the speech and noise power spectral densities. Assuming that the normalized speech and noise correlation vector follow multivariate Gaussian distributions, a maximum likelihood estimator for the normalized speech correlation vector was proposed. This estimator depends on estimates of the a priori SNR and on the normalized noisy speech correlation vector. The normalized noise correlation vector gamma n is here replaced by a constant, a time and frequency independent mean normalized noise correlation vector, given by the frame overlap and the STFT analysis window. In this work, using the assumption that speech signals can be modeled by a low-rank model of rank Q, we propose a subspace-based normalized speech correlation vector estimator, based on the subspace decomposition of the pre-Whitening normalized noisy speech correlation matrix. Further, instead of using a fixed time and frequency independent value for rank Q, we estimate Q per time frequency point based on the a priori SNR estimate. Similarly to the vector formulation of the normalized noisy speech correlation vector, we defined the normalized noisy speech correlation matrix gamma y as a function of the normalized speech correlation matrix gamma x and the normalized noise correlation matrix gamma n and the a priori SNR C, where gamma y is the correlation matrix Ry normalized to the first entry of this correlation matrix. Similar yield for the speech and noise correlation. Now, decomposing the normalized noise correlation matrix gamma n using the Koleski decomposition and applying this to the normalized noisy speech correlation matrix, we obtained the pre-Whitening normalized noisy speech correlation matrix depending on the a priori SNR and the pre-Whitening normalized speech correlation matrix gamma xw. Further, let the eigenvalue decomposition of the pre-Whitening noisy speech correlation matrix given by the sum of the noisy speech eigenvalues lambda y and the orthonormal eigenvectors b, such that the noisy speech eigenvalues are hence related to the speech eigenvalues lambda xw and the a priori SNR C. Solving this formulation for the speech eigenvalues, so lambda xw, and assuming that the speech signals can be described by a low-rank model of rank Q, we propose to estimate the pre-Whitening normalized speech correlation matrix using the Q largest eigenvalues and corresponding eigenvectors of the pre-Whitening noisy speech correlation matrix. The subspace-based normalized speech correlation vector estimator is then obtained by transforming the pre-Whitening or the estimated pre-Whitening normalized speech correlation matrix back from the pre-Whitening domain and normalizing this to its first entry. To implement the proposed subspace-based estimator, an estimate of the dimension of the speech subspace Q is required. Since most of the existing estimators of the dimension of the speech subspace Q have a larger variance in Q when using a small number of analysis data, as for multi-frame approaches, in this work we either use a fixed time and frequency independent Q or estimate a time and frequency dependent Q using an a priori SNR based threshold estimator. First, to set Q to a fixed value, we assume that the uncorrelated speech component x prime can be neglected, such that the speech correlation vector x is only given by the temporally correlated speech component, which is of course not the case in practice. However, Using this assumption, the speech correlation matrix becomes a rank 1 matrix, and we set the dimension of the speech subspace for each time frequency point to 1. Second, we use an a priori SNR-based threshold estimator, similarly to the one proposed by Hendricks et al. Given a threshold, delta, depending on the a priori SNR estimate, C, the dimension of the speech subspace is given by the cardinality of the set of estimated noisy speech eigenvalues that are larger than this a priori SNR-based threshold delta. For the evaluation, we use 250 seconds of speech material from the TIMID database. As noise signals, we used 4 noise types: babble noise, modulated white Gaussian noise, traffic, and speech-shaped noise. The SNR was ranged from -5 to 20 dB in 5 dB steps. We use a sampling frequency of 16 kHz, a frame length of 4 milliseconds, and a frame shift of 1 millisecond, resulting in an overlap of 75%. We set the number of consecutive timeframes L experimentally to 6, resulting in 9 milliseconds of analysis data. To estimate the a priori SNR, we use a decision-directed approach with the speech present probability-based noise PSD estimator. The pre-widening transform is performed using a time-independent but frequency-dependent pre-trained normalized noise correlation matrix. We compare the performance of the normalized speech correlation vector estimators for the multi-frame Mvdr filter, either using the state-of-the-art maximum likelihood estimator, the proposed subspace-based estimator with Q equals 1, and the proposed subspace-based estimator with the a priori SNR-based threshold estimator for Q. As a reference single microphone speech enhancement algorithm, we use the Wiener gain with an equivalent frame length of 9 milliseconds and an overlap of 50%. We evaluate the filters in terms of objective speech quality using delta PESC, in terms of noise reduction using the segmental noise reduction measure, and in terms of speech distortion using the segmental speech SNR measure. The figures depict the results averaged over all speech and noise files for each SNR. First, it can be observed that the multi-frame Mvdr filter using the subspace-based estimator for Q equals 1 results in the worst results over all SNRs. Further, in terms of PESC improvements, the multi-frame Mvdr filter using the proposed gamma XQ outperforms all other filters for SNRs up to 15 dB. In terms of segmental noise reduction, the multi-frame Mvdr filter using the proposed gamma XQ achieves clearly better results than the maximum likelihood multi-frame Mvdr filter. In terms of segmental speech SNR, the multi-frame Mvdr filter using the proposed gamma XQ leads to a similar performance as the multi-frame Mvdr filter using the state-of-the-art maximum likelihood estimator. Further, the multi-frame Mvdr filter using the proposed subspace-based estimator yields a lower segmental noise reduction and segmental speech SNR than the traditional Wiener gain, resulting in a better objective speech quality for SNRs up to 15 dB. Let's summarize this paper. We propose a subspace-based normalized speech correlation vector estimator for the single microphone multi-frame Mvdr filter. This estimator based on the assumption that speech signals can be modeled by a low-rank model of rank Q. We estimated the normalized speech correlation vector based on the Q largest eigenvalues and eigenvectors of the pre-widened normalized noisy speech correlation matrix. The rank Q is estimated per time frequency point based on the a priori SNR estimate. The simulation results showed that the multi-frame Mvdr filter using the proposed subspace-based estimator leads to a better speech quality and more noise reduction than the state-of-the-art maximum likelihood approach, where speech distortions are kept low. So thank you for watching this video. If you have any questions, please send me an email. Please stay safe and goodbye.